All right, so this video, I figured I would just draw it out for you because it's kind of drawing intensive, but you can definitely take a look at the slideshow. It's only 4 or 5 slides for this next part. So this is a special case of refraction. And to start with, I'm going to have you imagine that you're at the bottom of a pool. Okay, so you're laying down here, holding your breath, the bottom of the pool, and you're trying to look up and see, whatever you can outside the pool. And the idea of this is, just for sake of argument, the water is up to the very top level of the pool. Okay, so let's say you're looking at this angle here. We draw our normal. So this is your theta, and this would be the incident angle because you're looking in that direction. Okay. And don't worry so much about looking versus seeing versus the direction of the light. We'll figure that out in a second. I just want you to have this visual, okay? So when you're looking at the bottom of the pool, what do you see? And we know that air up here is a fast medium versus water being a slow medium. So the light is going to bend, all right? And really what you're seeing is light coming in this direction, okay? So you're seeing this bending closer to normal here, but it's bending away from normal if you're following the light in the opposite direction, which is what I want to kind of focus on. I want to call this our refracted and this our incident angle. And what I'd like you to do is try in your calculator to set up this equation, and everybody will do this separately, on their own time. But remember, Snell's law is N1 sine theta 1 equals N2 sine theta 2. And if we plug in on our one side here, this is 1 and this is 2. If we do the N of water is 1.33, and the sine, let's pick 15 degrees as our first one. Sine of 15 degrees equals N2 is air, which is an N of 1, times the sine of theta 2. If you solve for theta 2, let me do that and make sure I'm in degree mode. Everybody should be back in degree mode for this. 1.33 sine of 15, inverse sine of that answer is 20.13 degrees. Okay, which makes sense. It's getting bigger. It's bending away from normal. What I'd like you to do now is continue with Snell's law and plug in 30 degrees into sine theta 2 and solve for what theta 2 would be. So if I do that, again, 1.33 sine of 30 degrees equals equals N2 sine theta. If I solve, this is 1. If I solve for theta 2, I do the inverse of that, and I get 41.7 degrees. So let's try theta 1 equal to, what did we just do, 30 degrees? Let's try 40 degrees and then 50 degrees. And we'll see what theta 2 is. Theta 2. Do it real quick. I wish I had done this beforehand. 1.3 sine of 40. We're teaching in real time. Inverse sine, answer, it's like 59 degrees. And when I do the same thing for 50 degrees, and I do the inverse sine, because I'm just using my calculator, I get, I made a mistake. And did I really make a mistake? Or did the calculator make a mistake? What's going on here? And you really want to think about it in terms of what's happening to the light. I was at, let's say, 15 degrees and it bent that much. I was at 30 degrees, it bent that much. I was at 40 degrees and it bent that much. When I went to 50 degrees, it blows up. Why is that? And mathematically, you'll know it. You're trying to do the inverse sine of a number that's greater than 1, which doesn't exist, right, on our unit circle. So that's mathematically what's going on. what we want to talk about today is the physics behind what's going on. And what you can do is you can work with your calculator and try and, via iterative approach, keep getting, bigger and bigger angles until you're basically, I'll draw it here, make this angle bigger and bigger until this is approaching 90 degrees. Once, what you'll see is if that angle, is too great, your calculator won't be able to give you an answer. So what you're really looking to do is to set this equation, figuring out what this angle has to be to make this angle be 90 degrees. So if we solve for that, theta 1 is equal to, theta 2, the sine of theta 2 is going to make this 1. So this goes away at 90 degrees. And inverse of, n2 over n1. So this special angle here, I guess we could go out on a limb and call it a critical angle. This critical angle here, where the light bends 90 degrees, is actually called that. It's called the critical angle. And for water, if we do this inverse sine, let me quit this because I still have my error. The inverse sine of n2, which is 1, divided by 1.33, which is n1, 1 divided by 1.33. If I do the inverse sine of that, I get 48.75 degrees. That's my critical angle for water to air. Sorry for the holiday motif here. Water to air, okay? So what happens if you're above that angle? And this is sort of the end part of what we're talking about here, the last thing. What you're going to get is as you approach that bending, once you get to the critical angle, anything above it is going to give you a reflection. So this angle and this angle will be the same because it's a reflection. And this is known as total internal reflection. Okay, so the light's trying to bend so much that it doesn't refract anymore, it reflects. So this is a refraction phenomenon, but it turns into a reflection. So I have some notes on the slideshow that'll help you with that. Also, maybe the drawings will be a little bit better, but not in real time. Some really powerful examples of this, and we always talk about this in class, is, well, probably the best one nowadays is Fios. For those of you that are lucky enough to have this internet service, this is based on fiber optics. And the way a fiber optic channel works is this is basically a glass fiber, and light is passed into it, and it's at such an angle that it can't escape the cable. So data is passed over light, which, as you can imagine, is probably pretty fast. That might be an understatement. So we'll talk more about this. I just wanted to maybe draw it out for you, and hopefully this was a little bit better than just looking at the slides.